Adding LLM-generated features to graph neural networks has become a standard practice. Pipelines like TAPE, GLEM, and LLM node bed report consistent accuracy gains on benchmarks like Cora, PubMed, and OGBANARXIV. The prevailing intuition is that LLM text descriptions provide rich semantic signals that complement graph structure and node attributes. But there's a gap in the literature. Most of these positive results rely on sophisticated integration mechanisms, joint training, variational M, prompt conditioning, or gated fusion modules. What happens if you strip all that away? What if you simply concatenate the LLM features to the original node features and train a standard GNN or MLP? We ran this direct comparison, and the result is counterintuitive. On homophilous benchmarks, pure input concatenation can systematically degrade accuracy. On PubMed, adding sqrt-encoded GLM features drops MLP test accuracy by 17 percentage points. On Cora, the drop is 4 points. On CiteSeer, it's negligible. Yet on medium homophily datasets like WikiCS and OGBANARXIV, the same concatenation strategy yields gains of 4 and 11 points respectively. This isn't a noise artifact. It's a predictable regime where LLM features interfere with the original signal. Today, we'll dissect this phenomenon, isolate the mechanism, derive a scaling law that predicts the cost, and show you how to remediate it. Let's start with the headline numbers. We're looking at the planetoid public splits, which use extremely few labeled nodes. PubMed has only 60 training labels. We concatenate a 384-dimensional sqrt encoding of GPT-4o mini-tape explanations to the original bag of words features. The MLP baseline using only original features hits 72.1% test accuracy. Concatenating the LLM features crashes that to 55.1%. That is a statistically significant drop, with a standard error of 0.3 percentage points. Cora sees a 4.3-point drop. CiteSeer sees a 0.6-point drop, which is within seed noise. But flip the script to WikiCS and OGBANARXIV, and we see positive gains. So the effect isn't that LLM features are universally harmful. It's that concatenation fails in a specific regime. Is this just a curse of dimensionality? If I add 384 dimensions of Gaussian noise to PubMed, accuracy drops by 37.3 points. The real LLM features only drop accuracy by 17 points. This means the LLM features contain signal. They rescue about 20 points of performance compared to pure noise. But they still lose to the original features. The LLM features are better than noise, but worse than the original bag of words representation in this setting. This suggests the interference is driven by the informational content of the LLM features, interacting with a finite sample penalty. To isolate this, we ran a controlled ablation on PubMed. We compared the LLM channel against zero padding, PCA of the original features, and Gaussian noise, all at the same 384-dimensional size. Zero padding causes no degradation, ruling out dimension mismatch. PCA of the original features causes a mild 2.3-point drop, showing that redundant self-information is relatively harmless. Gaussian noise causes a massive 37.3-point drop. Real LLM features sit in between at 17 points. Having the weight decay doesn't change the 17-point drop, ruling out regularization artifacts. The mechanism is specific to the LLM features content, and it sits on a spectrum between self-information and pure noise. So why does this happen? The key is the label budget. The planetoid splits provide very few labels relative to the input dimensionality. We derived a scaling law that quantifies this. The concatenation cost scales with the square root of the LLM dimension over the number of training labels. Specifically, we fit a power law to the cost, and it collapses onto a single surface with an exponent of 1.31. This holds across different training fractions. When we sweep the training set size from 60 labels up to nearly 10,000, the cost decays monotonically. At 60 labels, the cost is 17 points. At 5,000 labels, the cost is less than 1 point. The 17-point drop is simply the extreme corner of a smooth surface where the dimensionality is high and the sample size is low. This scaling law also explains why the effect attenuates on larger splits. Under random 50-25-25 splits, which provide thousands of labels, the PubMed drop compresses to less than half a percentage point. The phenomenon is a finite sample overfitting effect aggravated by the LLM channel, not a data-specific artifact. Now, how do you predict when concatenation will help versus hurt? We looked at homophily, but that's a weak predictor. The correlation between concat cost and homophily is near zero. The operative variable is the standalone discriminability of the LLM features. We define this as delta sig, the accuracy gap between an MLP trained on LLM features versus an MLP trained on random features. Across 9 datasets, we found a threshold on delta sig that separates the regimes. The bootstrap S change point is approximately 13.8 percentage points. If delta sig is below this threshold, concatenation predicts a non-positive cost. If it's above, concatenation predicts a positive cost. This rule classifies 7 out of 9 datasets correctly. On PubMed, delta sig is low, so you get hurt. On WikiCS, delta sig is high, so you win. The two false positives are both below 1 percentage point, effectively neutral. Homophily alone cannot predict this. Delta sig is the screening variable. What if you're forced to use LLM features? Can you fix the interference? We tested cheap input-side regularizers. LayerNorm makes things worse, dropping accuracy by an additional 15 points. This is because LayerNorm rescales the LLM directions to unit variance, removing the natural magnitude cues that the small sample classifier uses to suppress noise. Dropout and linear projection help somewhat, recovering 36 to 45% of the gap, but they don't match the baseline. The most effective remediation is to drop the LLM channel entirely. The original features strictly dominate every learned cheap fix. However, if your downstream pipeline structurally requires the LLM presence, a learnable scalar gate is your best option. You multiply the LLM features by a learnable scalar initialized to 0. This gate recovers 89% of the raw concatenation gap. But there's a catch. Even the gate can overfit. If you train the gate to the full loss minimum without early stopping, the scalar value drifts up and performance collapses. The gate acts as a regularized version of dropping the feature, selecting a small non-zero weight that trades a tiny generalization penalty for the LLM signal. Finally, how does this reconcile with the aggregate benchmarks reporting gains? It doesn't contradict them. It sharpens them. The gains reported in tape, GLEM, and LLM node bed rely on joint training, selector modules, and prompt engineering. Our Shapley decomposition shows that when you average overall coalitions, the LLM contribution looks positive but small. But the direct contrast reveals the interference. The integration machinery in those pipelines provides the inductive bias that raw concatenation lacks. Raw concatenation is just the first step, and on its own, it can backfire in the few-shot regime. So the practical guidance is clear. If you're working on a few-shot homophilous graph with a small label budget, check deltasig. If it's low, pure concatenation is a liability. The best move is to drop the LLM channel. If you must keep it, use a learnable scalar gate, but monitor the gate dynamics and use early stopping. And remember, the 17-point drop on PubMed is a predictable finite-sample effect governed by the scaling of dimension over sample size. Understanding this regime helps you build more robust, predictable pipelines for LLM-enhanced graph learning. Thanks for watching. If you're interested in the code and the full ablation tables, they'll be released upon publication. Keep building.